In the last class, we started our study of filters, and we started off trying to figure out how to achieve or how to obtain what's called an all-pole filter, right? Remember that any transfer function is a ratio of polynomials in S, and to make our life simple, we said, okay, let's assume that the numerator polynomial is just simply 1, and we'd like to find what the denominator polynomial must be, so that the magnitude response of this transfer function, which is simply 1 over d of s times d of minus s evaluated at s equals j omega, must approximate this. So, in other words, the squared magnitude response must approximate the ideal brick wall, and since the magnitude squared of any transfer function is simply an even function of omega, it must follow that the denominator polynomial must be an even polynomial. So, it must be a polynomial in omega square, and it stands to reason that there must be n coefficients that appear in the denominator. And we denoted this part of that denominator squared polynomial by f of omega square, right, signifying the fact that the function is a function of omega square. Now, if 1 over 1 plus f of omega square approximates or is attempting to approximate the ideal brick wall, it follows that f of omega square itself must approximate this function here, where it is 0 in the range omega equal to 0 to 1 and becomes infinity thereafter, right. And we said, oh well, one way of doing this is to basically use what's called the maximally flat approximation, where you basically say f of omega square is omega to the power 2n, right. And as we saw yesterday, as we at DC, of course, f of omega square is 0, and as omega keeps increasing, f of omega square is as flat as possible about which point? It is as flat as possible about DC. I mean, there is nothing holy about DC. In principle, we could have moved the maximally flat point to someplace else in the passband, which corresponds to 0 to 1, right? But traditionally, this is how this stuff came about. They said f of omega square is omega to the 2n, and this will give us magnitude response where mod of h of j omega whole square is 1 over 1 plus omega to the 2n. And this approximation is what is called the maximally flat or the Butterworth approximation, and such filters are called Butterworth filters. And if you plot the squared magnitude response, it will turn out, as you can imagine, that if this is 1 and this is 1, what is the magnitude response? Regardless of n, the magnitude response squared at omega equal to 1 is what? It's half. So, magnitude squared is always associated with power. So, that is the half power frequency. If the squared magnitude is half, what comment can we make about the magnitude itself? 1 by root 2, which is the 3 dB frequency, right. So, in other words, the bandwidth of the filter, a 3 dB bandwidth, is simply 1 radian per second. Does it make sense? And so, for different values of n, so for n equal to 2, for instance, let us say this is the one for n equal to 1. N equal to 2 will be flatter in the pass band and sharper in the stop band, and as you keep increasing n, you will eventually achieve the ideal, right. So, this is increasing order. Does it make sense? All right. So, that's as far as the approximation is concerned. Now, but that's not really, that's only part of the puzzle. What we are actually interested in finding is, we'd like to find the h of s which corresponds to this magnitude response, okay. And how do we get to the magnitude response here? Given h of j omega the whole square, how do we get back to the magnitude response? How do we get back to the transfer function? Well, we saw yesterday that replace omega square with minus s square, and then so what do we end up with? So, we basically get 1 plus omega square is minus s square whole power n, okay, and this must be equal to 1 over, what is that? That's nothing but d of s times d of minus s, right. And therefore, what is our job now? We find, how do we find d of s? Well, we find the roots of, so find the roots of d of s times d of minus s, and the poles of d of s, or the roots of d of s, and roots of d of s in the left half plane are what we are interested, because we are interested in realizing a stable filter transfer function. Well, now that we know this, it's just a matter of start doing the stuff. So, n is 1 is trivial. So, you have 1 by 1 minus s square, which is 1 over 1 minus s into 1 plus s. So, which is the stuff that we discard? We discard that. So, h of s is 1 over 1 plus s. All right. So, let us come to something which is a little more interesting. N equal to 2, mod h of j omega square is 1 by mod h of j omega the whole square equals what? 1 plus omega raised to the power 4, and therefore, when we replace from here, we get to 1 by 1 plus minus s square whole square, right, which is basically 1 by 1 plus s power 4. We need to find the roots of 1 plus s power 4, and what are the roots of s power 4 equal to minus 1? Yes. Oh, it's minus s power 4 equals minus 1. Yeah. So, what are the roots? Where are the roots located at? Pardon? Yeah, pi by 4. They all lie on the unit circle, right? You'll have to assume this is a circle. So, we have a root there. If you have a root there, you will have a root there. We already know that if h of p is a root, minus p is also a root, and minus p star will also be a root. We have 4 roots, all right. And which 2 roots are we interested in? The left half plane. So, we are interested in these 2 roots, and remember, what is this angle? 45 degrees. So, what are the poles that we are interested in? P1 is what? In Cartesian form, minus 1 by root 2 plus j times 1 by root 2, and P1 star is of course the conjugate of this. So, what is the polynomial? This is the root, right? We know the roots of the polynomial. How do we, what is the polynomial itself? So, this is, remember, this is d of s times d of minus s. So, what is the polynomial? It is s plus 1 by root 2 plus j by root 2 times s plus 1 by root 2 minus j by root 2, and that is simply nothing but, yes, please do the math. This is nothing but s square plus root 2 s plus 1. All right. So, this is d of s. Remember, we got a little bit lucky because when s is equal to 0, this automatically becomes 0. Otherwise, you will have to have a coefficient here, which basically makes sure that the denominator polynomial is 0 when when s is 0, here this becomes automatically 1, right. Otherwise, you will have a constant of multiplication where which you may, and then that constant is derived, so that when s is equal to 0, you get 1. Okay. So, this is so therefore, the second order Butterworth filter has a transfer function which is the form 1 over 1 plus root 2 s plus s square. Okay. And what is the 3 dB bandwidth? This is 1 radian per second. Okay. So, in general, if you want omega c radians per second, what would we do? Simply replace s with s by omega c. All right. Now, this is I am sure you are aware of the standard form of writing a second order transfer function, and in the standard form is is 1 plus s by omega p q p plus s square by the standard form of a second order all pole section. Okay. So, simply looking at these two, what do we see as comparing these two? What comment can we make about omega p? 1. And what about qp? 1 by root 2 or 0.707. Right. So, will there be overshoot or will there be no overshoot in the step response? There will be overshoot. Why? The q is greater than half, and therefore, there will be overshoot in the step response, right. It turns out that the overshoot is about 4%. Anyway, so that is again, as you can see, the second order Butterworth filter is also very straightforward, and therefore, similarly higher order filters, I am just going to do the third order one and stop. So, now there is no point in going through the same rigmarole all over again. D of s into d of minus s is what now? 1 minus s bar 6. So, where the roots are basically, again we have our circle, all right, and where are the roots? There must be a root at obviously at -1 and +1, and then you divide the whole pizza pie into 6 slices, right. So, you basically have something there, and and therefore something, right? And this is what is this angle? 60 degrees. So which are the poles that we are interested in? Those in the left half plane. So there is basically a pole at. So what is the polynomial? So there, the poles that we are interested in are at what locations? There's one at -1, right? Then -1/2 plus minus j √3/. All right. So therefore, the polynomial is simply s plus 1 times s plus half the whole square plus three by 4, right, which is 1 plus s times 1 plus s plus s. So therefore, the third order Butterworth filter h of s is simply given by 1 over 1 plus s times 1 plus s plus s. And what comment can we, so you can think of this obviously as a cascade of a first order section and a second order section. And what comment can you make about the location of, I mean, if you express the second order section, this second order section in standard form, what comment can we make about the omega p? Omega p still remains 1. And what is the QP now? QP is 1. Okay. So it would be interesting to kind of compare the response of the second order Butterworth and the third order Butterworth. This is 1, and this is half. And the second order Butterworth squared magnitude transfer function probably does something like this. Right? Now, the third order transfer function does something, I mean, I'd like to express this as simply the product of the magnitudes of the first order response and the second order response. So, what comment can you make about the first order response? How does that look like? The squared magnitude response of the first order part of that third order transfer function. How would it look like? Yeah, so how would that, like, if you draw that, what would, how would it look like? Compared to this black curve, how would that look like? Yeah, it will be more gradual. It will start at the same point and then it will also go through do something like that. What comment can we make about the second order section? Pardon? So, okay, let's start at the origin. What will it be at the origin? 1. Okay, slightly beyond omega equal to 0, how will it look like? Huh? Okay, the one answer I got was, oh, it will be flat. Okay. So, remember, the total response is the product of the first order response and the second order response, right? If the second order response is flat and the first order is falling, what if you multiply the two, what will you get? Something which is falling, right? But the third order response is actually, how does the third order Butterworth response behave at the origin? It is flat. So if the first order section has a response which is falling, it must follow that the second order section must have a response which is going up, right? So the second order response will basically should be expected to do something like this, right? And the overall third order response will look like what? Should look like, how will it be compared to the second order Butterworth response? It will be even flatter than the second order one, so it will probably look like this, right? And the overall response is the product of the first order response and the second order response, and therefore the second order response must look like, how will it look like? Pardon? It will have a magnitude of 1 at omega equal to 1, right? But more importantly, okay, so here it will have a magnitude of 1, right? So it starts off like that, and eventually what does it do? Eventually the second order response falls off as 1 over omega square, correct? So eventually the second order response must do this, must do something like this, okay, all right. And so therefore it starts off going this way and eventually is falling off in the middle. What must it do? Well, there must be a peak. Bad picture, but I'm sure you get the idea.